This is the 32nd video supplement for CIS 351, Grand Valley State University's course on Computer Organization and Assembly Language. This video discusses immediate parameters and MIPS I-Type instructions. Videos 29 and 30 show how to build a CPU that can execute a sequence of arithmetic instructions where each instruction takes two registers as input and puts the result in a third register. In this video, we add support for instructions that take as input one register and a literal value. This hard-coded literal parameter is called an immediate parameter because, as we'll see, this value is stored immediately in the instruction. In contrast, the other parameter is classified as register direct because that data is stored inside a register. The first thing we need to do is design the machine instruction. That is, we need to clearly understand how each bit in the instruction is used so we can correctly route that information throughout the CPU. Let's begin by reviewing the R-type machine instruction. It consists of an opcode, followed by the 5-bit numbers for each of the two source registers, and then the 5-bit number for the destination register. R-type instructions also contain a 5-bit shift amount and a 6-bit function code. In their textbook, Patterson and Hennessy list 4 design principles. Simplicity favors regularity, make the common case fast, smaller is faster, and good design demands good compromise. Each of these 4 principles will come up in discussion as we add components to the CPU. At the moment, the most relevant principle is the first one. Simplicity favors regularity. Actually, I think it makes more sense phrased this way. Regularity promotes simplicity. In other words, the more similarity there is between a CPU's components, the simpler the hardware will be. This simplicity leads to chips, which in most cases are smaller and use less power. In addition, simpler chips are often easier to design, leading to fewer bugs. The simpler something is, the less likely you are to make a mistake designing it, and the more likely you are to find any mistakes you did make while you test it. So with that in mind, let's see how much of the R-type instruction format we can reuse. Well, we certainly need an opcode. So let's keep that in the same place for both instruction types. There's no good reason to add complexity by putting it somewhere else. We also need one source register and one destination register. We don't need space for a second source register, a shift amount, or a function code. Therefore, these bits are available to be used for the immediate value. Now at this point, we could strictly apply Principle 1 and use what we see here as our R-type instruction format. But splitting up that immediate value seems kind of silly. So we'll apply Principle 4, good designs demand good compromise, and reorganize the I-type instruction like this. Notice specifically that we've consolidated all the bits for the immediate value and put them at the end. Another way to look at it is that we are willing to use those aspects of the R-type instruction format that also clearly make sense for the I-type instructions. But we're also willing to compromise and allow for differences between those two formats when doing so leads to a better overall design. So now let's see what changes we need to make to the CPU to support these I-type instructions. Here's our current CPU, and we want to add support for instructions that look like this. The fundamental change we need to make is that we need to get the immediate value from the instruction to the ALU. But now we have a small problem. We have 2 competing values for the ALU's second input. How do we connect both to the ALU? Well, we use a MUX, which raises the next question. What determines the value on the MUX's selector wire? Or in other words, what tells us whether the ALU should be using a value from the register or whether it should be using an immediate value? Well, the opcode. In general, the purpose of the opcode is to tell us what operation the machine should be performing. In this case, the opcode is what tells us whether we should be doing an R-type add or an I-type add-I. It's helpful to abstract this decision by adding a circuit that takes the opcode as input and chooses the correct value for the MUX's selector wire. This piece of hardware is called the control unit because it controls what the CPU does during any given instruction. The control unit's outputs are called control wires. This first control wire we've added is called the ALU source because it determines the source of the ALU's second input. This isn't the only change we need to make so that the CPU handles both R-types and I-types. What other modifications do we need to make? There are actually several. First, notice that the ALU's operation is no longer determined exclusively by the function code in bits 0 through 5. Unlike R-type instructions, each I-type instruction, add I, and I, or I, and so on, has a unique opcode. This means that both the opcode and the function code determine what operation the ALU should perform. To handle this, we add the function code as an input to the control unit and give the control unit the responsibility of telling the ALU what to do. Next, notice that the R-type and I-type instructions store the destination register in two different places. R-type instructions store this information in bits 11 through 15, whereas I-type instructions store this information in bits 16 through 20. So, how do we get the correct value to the register file's A3 input? Oh, another MUX. This MUX, of course, needs a selector wire, which is driven using an additional control wire. This control wire is called the register destination because it determines which value is passed as the instruction's destination register. The last change is a bit subtle. Remember that we're building a 32-bit CPU. That means that the ALU's inputs are each 32 bits. But the immediate value is only 16 bits. So, how can we turn a 16-bit value into a 32-bit value? And because these are signed values, it's not as simple as adding a bunch of leading zeros. To keep things simple, let's use some smaller numbers. For example, let's think about how we can turn a 4-bit signed value into an 8-bit signed value. Let's start with 2. 2 as a 4-bit number is 0010. To extend it to an 8-bit number, we just add leading zeros. This, of course, works for any positive number, just like we can add leading zeros to any base 10 number. But now consider -1. Adding leading zeros doesn't work because the result ends up as 15, not -1. So what is -1 as an 8-bit 2's complement number? Oh, 11111111. In this case, we had to add leading ones, not leading zeros. This use of leading ones applies to all negative numbers. This process is called sign extension because what we're doing is we're taking the sign bit and extending it to fill as many additional bits as necessary. So we use this idea to fix this type mismatch that we have, or wire size mismatch if you prefer, by adding a circuit called a sign extender to convert the 16-bit immediate parameter into a 32-bit value for the ALU. So now we have a CPU that can perform sequences of arithmetic and logic instructions. For now, those instructions can take one of two forms. The first type takes as input values in 2 registers, and we call this type R-type or register type. The second type takes as input a value in a register and another value stored immediately in the instruction. We call these I-type or immediate type instructions. These different instruction types are formatted differently because they need different types of information. Therefore, we added a control unit which determines the type of the instruction and also places values on control wires to direct how the CPU processes the instruction. In the next video, we'll see how to program this CPU using assembly language.